Hi, welcome everyone. There can be a slip between the cup and the lip, they say, and my colleague Professor Gokhale from India could not get his visa in time, and so because of that I am presenting him virtually and trying to coordinate with him the audio. Of course, he is not present, he gave a recorded speech and both of us coordinated once we have tried, and this is going to be talking about autonomous vehicles. You need to be doing everything remote, looks like. So, here we go. I will start his recording, and then in between if things do not work, then I will try to interject and put everything. Otherwise, we will go keep continuing till it lasts, and at the end I will field question and answers whatever you have, and we will move on. So, here I am going to start his recording as we planned. So, let us hope everything comes clean. Start.
Thank you, Prakash. The session today is titled Vehicular Technology and OpenStack NFV, which is jointly presented by me, Jayanti Gokhale, and Prakash Ramchandran. The objective is to highlight the current state of autonomous vehicular technology and how OpenStack components can be used to realize an OpenStack edge stack implementation. Next slide, please. The agenda for today's presentation is what is vehicular technology, and out here we shall look into the intelligent part of vehicular technology. Next up, we shall look at a few VT use cases in the context of connected vehicles and autonomous vehicles which are wrapped with IoT and onboard entertainment use cases. Subsequently, we will look at what is OpenStack's edge computing infrastructure, especially for small and medium footprints. Then we shall deliberate on how VT uses NFV, how VT uses NFV Mano to manage edge stack. Lastly, we shall also look at using OpenStack Edge for connected vehicle architectures and mapping OpenStack components for CVA use case. We shall end the session with some indicators for the next steps and final concluding remarks. Can I have the next slide, please? So, what is vehicular technology? It's all about use of technology for transportation and logic enablement. In the context of automobiles, it truly means making automobiles totally auto, like the autonomous car or the self-driving car. So what does it really mean? Present-day automobiles are equipped with a wide number of sensors that continuously monitor the state of the vehicle. An onboard computer processes this data and decisions are taken to control the vehicle and ensure a smooth, safe ride. However, in the present day, this is not just enough. We are looking at more insights. We try to draw more information from this vehicular data, and we wish to share this with other vehicles too. Share the data with surrounding elements on the road to create what we call it as a connected vehicle architecture is now gaining significance. So, vehicular technology for automobile and autonomous vehicles involves setting up a communication infrastructure like the use of radar, Lidar, SRDC, which are predominantly for vehicle to vehicle communications and vehicle to roadside equipment communications. Vehicles have an onboard unit We call this as an OBU, and this is responsible to manage the data processing required within the vehicle and also manage the vehicle-to-vehicle communications. The vehicle-to-vehicle communications are called as the V2V communication. The OBU also interacts with the roadside unit. A roadside unit is a unit which is normally set up on the roadside, typically at traffic intersections, and this is used to communicate with the data centers and other infrastructure. So we shall see more about the vehicle to vehicle and the vehicle to infrastructure communications a little later as we proceed in the talk. The second most important component happens to be the cloud environment or the cloud systems. And this will be a scalable computational infrastructure that computes on the sensor data and responds with precise calculations. And these calculations have to be with guaranteed response times. These response times are very stringent and they have to manage the steering and the driving decisions. The third aspect is the support for location maps, route maps, and traffic pattern information. This dynamic transportation data should be stored for navigational purposes. Mind you, part of this data could be static, and the traffic pattern information, which is dynamic, has to be overlaid on top of the static information. So the static and dynamic data can be stored in the Openstack Cloud and can be used for analytics as well. The fourth aspect is the existing OpenStack modules and the evolving edge standards to enable local as well as global decision making computational is possible. The LTE release 12-14, PC5 and LTE5 standards ensure devices meeting these standards are easily integrated into the IoT framework. Now the question is, why are we doing all this? What do we gain out of this? If you look at some statistics, we find that each year billions of dollars are lost, wasted, and wasted in various aspects of transportation systems, like losses due to accidents, losses due to delays in transit, losses due to wasted fuel burnt at signals, losses due to improper routing, and so on and so forth. Now the idea is that hopefully autonomous vehicles ecosystem will ensure a massive saving in this direction. In addition to the saving, it will also play a very important and a vital role in ensuring the safety aspects of the vehicular movement. The next slide, please. The impact of intelligent transportation systems can be seen on three aspects. The first aspect is about safety. We wish to minimize the accident rates, and this can be made possible by having some advanced information about the traffic pattern, information about the crossing patterns, etc. The second aspect is of mobility, and the third aspect is on something related with the environment. Now these are the three aspects of intelligent transportation systems, and applications are being built around these three aspects. If you notice, the costs that are involved are very, very high. The impacting costs are also very, very high, and intelligent transportation solutions attempt to minimize these costs and contain these costs. Next slide, please. Present day automobiles are equipped with a wide gamut of sensors, and these sensors detect the surrounding objects, detect obstacles, detect the surrounding scene, identify the terrain, detect the location, measure the speed, and also identify the direction of movement. In essence, all the sensors work in unison to identify the current state of the vehicle. Now, for example, Lidar allows us to prepare a 3D contour map surrounding the vehicle, while the radar determines the surrounding obstacles and determines the speed of the vehicle and also the speed of the neighboring vehicles. A GPS equipment with pre-built map information and inertial navigation system allows us to determine the vehicle's position, orientation, speed, and other aspects very precisely. Vehicles are equipped with high resolution cameras which grab the surrounding pictures and also capture video, which can be used for scene analysis and subsequent image processing. DSRC happens to be the main communication infrastructure that allows the onboard unit to communicate with other vehicles, and this gives us to the rise of V2V communication, and this is also used for communication to the roadside equipment, which we call it as the V2I or V2R communication. Please understand that all this infrastructure, in addition to the advanced electronics to manage the sensors and the actuators on the vehicle to achieve the basic drive functionalities, has to be integrated very well so as to achieve the automated vehicle functionality. Next slide, please. Autonomous vehicles hence have to carry this augmented infrastructure, and this augmented infrastructure demands high-end computing power on the board. Normally, a multi-core high-end compute infrastructure with real-time responses is what is implemented, and that happens to be an obvious choice. This also should be supported with computations at the roadside equipment and low latency computations at the backend infrastructure. So this becomes a good use case for a hierarchically defined edge computing and OpenStack implementation. Next slide, please. Let's look at the communication aspects of the AV. Each vehicle communicates with the surrounding vehicles in the same lane and across the lanes. Each vehicle is now acting as a node in a communication network which is mobile, and hence the topology becomes purely ad hoc. Such a networking technology applicable to vehicles or an ad hoc vehicular infrastructure for communication is now called as a VANET or Vehicular Ad Hoc Network, which is derived from the MANETs. A VANET is a technology which uses moving vehicles as the communication nodes, and this creates a mobile ad hoc network where each node acts as a node as well as a router connecting over to other vehicles, typically within a 100 to 300 meter range of each other, and thus creates a wider network. The routing decisions are obviously taken in an ad hoc manner from a hop to hop basis. The vehicular technology supporting for signaling, message routing and node management is also implemented in VANET. VANET also provides for vehicles or the nodes to drop off and join the network dynamically. Advancements have now been made possible in VANET to realize naive and intelligent form of message routing across the nodes. Can we have the next slide, please? The VANET provides networking environment which can be described at three major levels. The data center, which provides the backbone infrastructure. The control network that provides communication support to the roadside units in the form of V2I and I2I communications. And the ad hoc road network, which ultimately creates the V2V part of the network. Now each of these layers can support multiple protocols and they function as gateways. However, the primary protocols happen to be DSRC, Wi-Fi and other telecom networks. For very short range interactions, we can also have the support of RFID and Bluetooth. In V2V communications, collision warning messages are essentially broadcast from vehicle to vehicle across multiple hops without the involvement of the roadside units. While in the case of V2R, the vehicle to the roadside equipment, warning messages are sent to the roadside unit and these are broadcast to all vehicles within a range. That's how the roadside unit acts as a gateway. Next slide, please. So in essence, the principal components participating in the overall AV realization are A, the OBU, the onboard unit, which manages the V2V communications and also the V2V, V2R messages to the roadside units. The second entity happens to be the RSU, the roadside unit. This roadside unit receives messages from vehicles and broadcasts them to other vehicles or the backend infrastructure. Mind you, the RSU can also implement additional functionalities and additional applications. The third infrastructure that is provided happens to be the internet gateway infrastructure, and this supports connectivity to large volumes of low velocity data. And they also provide connected applications for the vehicle. Now something like entertainment applications and communication, mailing applications and so on and so forth. The next slide, please. As we mentioned earlier, DSRC happens to be the prime communication technology that is used in AVs. DSRC is an 802.11p wireless protocol, which is an extension of the 802.11 standard that operates on the 5.9 GHz licensed band. And this offers about 7 channels of communication, each of maybe a 10 MHz channel bandwidth, and offers speeds ranging from 6 to 27 megabits per second within 1,000 meters of coverage. The communication infrastructure has a very simple physical layer and a MAC layer implementation, and hence can be easily realized in electronic hardware. DSRC now becomes the baseline infrastructure for V2V as well as the V2I communication. As I mentioned earlier on, we can also have Wi-Fi, Bluetooth and RFID support in addition to DSRC. Next slide, please. Now this slide depicts the complete communication mechanism showing the V2V, V2R and V2I interactions, and this essentially forms the core communication mechanism to support automated vehicles or the intelligent vehicle system, IVS as we call it. The next slide, please. Let me make a few more words of mention about DSRC. The V2V communications implemented on the onboard units meant for short-range vehicular networks which use DSRC provides a fast and reliable communication for real-time safety applications. DSRC does not really suffer from vehicle shadowing, and hence it allows us to communicate with other vehicles or other RSUs. There is no issue of oversized vehicles shadowing smaller vehicles. The main issue, however, happens to be the stringent response times, and by which we mean we need to have a scenario wherein the vehicles can react within an allowable maneuverable time, and this happens to be something of the order of about 4 to 8 milliseconds. Another challenge, however, is the way we identify and address vehicles. Now, onboard units cannot be assigned an IP address, especially because they are purely ad hoc and they are mobile. Hence, we used a centralized third-party certificate of authority to assign a unique identity, and this identity is tagged with the vehicle's number plate. So, each OBU has a valid certificate, and based on a digital signature that is sent by the OBU, using public key decryption, all the messages are verified at the receiver's end. So this is how we ensure identity and message transmission between vehicles. Next slide, please. V2R and V2I communication uses the existing network infrastructure such as wireless access points and the RSUs, and these provide a long range network. So these RSUs act as the gateway to the underlying mobile roadside vehicle network. The roadside infrastructure could be built over an existing communication infrastructure like a telecom infrastructure, 5G and 4G, or any other backbone infrastructure. It could be even fiber. Also, this can provision some middleware support and computational infrastructure for some applications. And hence, this becomes a good candidate for OpenStack implementations. So the roadside unit is not just only a communication entity, but it will also have some compute infrastructure as well. Next slide, please. The DSRC messages originating from every vehicle, it broadcasts to all vehicles in the surrounding. A scheduler is implemented in every OBU, which uses a preemptive policy for high priority messages. The messages are primarily categorized as what are called as basic safety messages, which are periodic messages sent approximately at a 10 Hz rate, and these give the details of the vehicle's status, like the vehicle's speed, the location, the acceleration, positional accuracy, etc., etc., etc. And all these messages are based out on the SAE-J 2735 standards. Now these happen to be periodic messages. In addition to these periodic messages, asynchronous messages are also sent as high priority messages, and these asynchronous messages indicate occurrences of events, a crash. So they typically indicate a bunch of event flags. They give information about obstacle information or traffic warnings. So all these messages are asynchronous messages. They are not periodic in nature. And as we mentioned earlier, each and every OBU has a valid certificate, and based on a digital signature and using public key encryptions, these messages are verified at the receiver's end. All these messages are once again relayed down, they are broadcast. Next slide, please. How are these messages routed? In V2V communications, the collision warning messages are broadcast from vehicle to vehicle across multiple hops without the involvement of the roadside unit. While in the case of V2R, warning messages are sent to the roadside units, and these are relayed, these are broadcast to all vehicles within a given range. We also have got a hybrid model which provides for both V2R as well as V2V messaging for the same message with the same event ID, which means for a given message there are alternate message delivery paths, and the receiving unit drops off messages once it has received a message with a given ID. Obviously, this ensures reliability and guaranteed delivery of message from one or multiple sources. Next slide, please. So let us now look at what is this connected vehicle applications. As I mentioned earlier, connected vehicle applications are broadly classified as safety applications, mobility applications, and environmental application. We will see details of this application in the subsequent slide. Next slide. This slide depicts the infrastructure for intelligent vehicles, and if you notice, the infrastructure is layered with the OBU residing in the vehicle, acting as the main source of information triggered from the sensors. The next level of data aggregation takes place at the RSU, which acts as the primary gateway. A group of RSUs are interconnected to a centralized controller called as a RSUC, the RSU controller. And this RSUC provides computation, storage, and the required networking infrastructure. These RSUCs are themselves interconnected, forming a high level network offering I2I interconnections. Infrastructure to infrastructure segments of the network are formed, and this becomes a good use case for edge cloud infrastructure. Each of the OBU, RSU, and the RSUC will be deployed with what are called as application units. Each and every application unit offers multiple application functions, and the application unit can be tagged to an underlying infrastructure requirements for compute, storage, and networking support. You will notice that this diagram also depicts a V2I interaction with mobile base station infrastructure. So it means there could be some applications which are running on board, and these applications could directly make use of the base station infrastructure, the mobile base station infrastructure. Next slide, please. In the context of the architecture described in the previous slide, the RSUC acts like a local data center with virtualized resources. Now, it is worthwhile mentioning the fact that these resources are not very, very large. So it's something like a small drill down version of a data center. And these resources should be having a capability to run multiple application units. And these application units can run in virtual machines. So the RSUC should have the capability to run multiple AUs in VMs, should have the capability of deploying AUs on demand and provisioning containerized instances of AUs. And to realize this, we need a VM, a VN, and a VS, which can be provided by a cloudlet-like infrastructure. This brings us to the fact that OpenStack components like Nova, Neutron, Cinder, Ceph, Swift become a minimal set of modules that can be deployed at the RSUC. The next slide, please. Let's quickly understand the deployment of RSUs on the field. The RSU deployment is based on the traffic densities. For dense traffic regions, they can be installed probably at every intersection point to provide a V2R communication. The V2R communication is realized through the onboard unit, and the onboard unit is tagged onto a dashboard antenna which is installed within a vehicle, and the dashboard antenna has a typical range of 50 to 80 meters. And that is the reason why for dense traffic densities we try to deploy an RSU at every intersection point. For normal regions, they can be installed every 200 to 350 meters given the range of an outdoor antenna for a moving vehicle, and for a very sparse region they can be installed every half a mile. This obviously calls in for an increased investment in the infrastructure. What about the RSUCs? A typical RSUC, however, can be attached and can be used to control and monitor anywhere between 80 to 100 RSUs. This slide depicts the connected vehicle applications for safety, mobility, and the environmental requirements. It is worthwhile to note the fact that all these applications are primarily low latency, location based, and moderate throughput applications which are executed at the edge. The applications broadly are classified as safety applications, mobility applications, and environmental applications. Safety applications are the things like curve speed warning, red light violations, pedestrian crossing warnings, warnings on oversized vehicles, and so on and so forth. Mobility applications are the ones which identify crash notifications so that this crash information can be propagated down and traffic patterns can be altered. Vehicle traffic operations to support traffic management and traffic operations. Applications regarding incident detection, applications regarding traffic signaling, smart parking, and these are some of the mobility related applications. Coming down to the environmental applications, maintenance, decision support systems, road weather warnings, electrical charging stations, management, etc. are a good use case. Next slide. I now request Mr. Prakash to take over and identify OpenStack resources and how they are mapped, consumed, and interconnected to realize connected vehicle applications. Over to Mr. Prakash. Thank you.
Thank you, Virtual Gokhale. It was a pleasure. It was great hearing all your expertise in the transportation area. Now let me move on to the OpenStack. I think Professor Gokhale has covered almost everything that was critical from statistics to the requirements, and challenge is how do we take an edge application and which is here for you, like connected vehicle applications, which definitely will be a mission critical use case for us. Already we are seeing that autonomous vehicles are being run, and with Lidar, Radar, and all those with the DSRC or short range communication along with the gateways. Now how do we bring it to OpenStack? That's a big challenge. So, and with the contentious demand that edge is, we want to own edge. So that's why I would say, I would call it open edge stack. Like OpenStack, we have an open edge stack. Let it be part of OPNFV, let it be part of ONAP, let it be Acrino. Anybody who wants to implement, fantastic. As long as we have something common and which we can realize within with a what you call even approximated way of doing currently till we have a better architecture to go by. So we have been struggling to map how do we do, where do we do. So what I did is I tried to partition and say that where do I put OpenIT Stack. The OpenIT Stack term was coined by Akraino. Akraino is the where Kandan presented even today, yesterday. He put the left side of the stack. If you look at the leftmost side, the AT&T, Akraino and Wind River, Intel, they bring together thinking that the open edge, whatever NFV infrastructure they need, that should be at the bottom. Then they have some middleware API exposed. Now when I say middleware API, that can mean middleware API for the Akraino in terms, their terms, it is application. So they are saying that the gap is there between the application and the infrastructure, and that can be run through middleware APIs. Go to the next block, second block. In the second block, I have been dealing with ONAP, management and network orchestration. They have their definition of what a ONAP edge they call it. I would rather say open edge. Let us call it open edge. They need some edge, and that can drive the open edge stack. Now, what is the open edge stack? We have to define our own in the terms of how is OpenStack going to address open edge stack. So, from the OpenStack point of view, what I view is you can have microservices. In fact, most of our implementations of Nova, Neutron and other modules have microservice APIs. They specifically address a unique object like compute object, network object, storage object. And so, what I see is we do have microservices architecture already. Now, if we expose these APIs specific to edge use case, that will be our goal. So, infrastructure exposed to the application and to the OSS, BSS, the MANOS, like the orchestration MANOS like ONAP, OpenBatten, OSM, Kubernetes has also become one of the orchestrators now for all purposes, and OPNFV for testing those. So, with the second block, what I am showing is the red blocks are the ones which are relevant to OpenStack in a way, but at the same time you remember going to the third, let me just come to third and fourth before I will address how we go about it. So, if I go to the third one, you see here mobility and session management. That is a 4G aspect, MEC, which is multi-access edge computing now called. So, that deals with the various radio accesses that are coming or even fixed network access. So, these two portions actually is partly going towards 5G, release 15. So, when Professor Gokhale said 12-14, he meant release 12, 13, 14, 15. Release 15 is what is current, and we are going towards 16 in the 3GPP. So, in those you will find that mobility management, session management, user plane function, those are all in the third block more related to futuristic 5G going towards it. And the last portion which I am addressing, policy. Policy is required everywhere, and we had some presentation on Open Policy Alliance, OPA, and then we do have Congress, and so we have to look at what language you are using, Datalog or Datapro, and Prolog and Datalog. So, Datalog is the one used. So, is it Datalog, and how do we go about having a third party policy controller being used, and there are two use from it, service policy, infrastructure policy. So, we have to address both, and infrastructure policy usually fan in directly into the red modules which I am showing. And lastly, of course, we need very fast computation for autonomous vehicle. If we move from the vehicle, the CVA, that is the connected vehicle application, towards autonomous vehicle, obviously we will need massively parallel processing and all those. So, those are the aspects. So, this generally covers most of the gamut, and I think we will discuss about this in the next session in Edge working group, that is at tomorrow in the morning and in the evening. 2 sessions are there, one led by Beth, one led by me. I look forward to your coming and joining us, and that is all I have for the time being. And what I will do is, if you have any questions, you can ask, we will wrap up otherwise. Anybody, any questions? I think we look forward to you joining us in the other session. I think I will take at this time end this session. Thank you very much for all coming and joining us.